Good afternoon, friends, and let's get started with another maths physics. Today is another chapter, that is magnets and Earth's magnetism. So this is the chapter what we are going to do today, and as you all know that I have already uploaded many important chapters of both maths and physics. So I would be requesting you, please go through those chapters also, because I'm uploading each and every chapter including the numericals of that chapter. Okay, so as you can watch that this is Parijat sir classes here, and as I'm continuing with a very important topic of the physics of class 12, we are continuing another class 12 topics of physics, and that is magnets and Earth's magnetism. Okay, so you are watching Parijat sir classes, and it's my request to like, share and subscribe my channel so that it can reach out to hundreds of the students, those who are not able to understand these chapters properly, and they can take the clues from here and get the chapter and the concept cleared. Okay, so let's get started with the chapter magnets and Earth's magnetism. Okay, first of all, you see here the force of attraction or repulsion between two magnetic poles of strength M1 and M2. Okay, so there is a magnet which has the pole. There are two magnetic poles of attraction or repulsion between two magnetic poles. So here is a magnet of pole strength M1, and here is a magnet of pole strength M2. Okay, and they are separated by a distance r. So what is the force of attraction between these poles? What is the force of attraction? So remember it is directly proportional to the product of the forces. As I can tell you here, it is directly proportional to the product of the forces, inversely proportional to the square of the distance between the poles. So if I combine and remove the proportional, we use a constant mu 0 by 4 pi. This mu 0 means it is the permeability of the medium. So here we are dealing in vacuum. Here we are dealing in vacuum. So that is why it is mu 0 by 4 pi, whose value is 10 to the power minus 7 Weber per ampere per meter. So the formula for the force of attraction or repulsion between two, if it is like poles, it is repulsion, and if it is unlike poles, it is the attractive force between the two poles of two different magnets, which is M1 and M2. Excuse me, and separated by a distance r between them. So this is the force of attraction or repulsion between these two forces, which are separated by a distance r. Okay, so if it is opposite poles, they will attract, and if it is like poles, it will repel. And please remember here, so we are using mu 0, 1 minute. So we are using mu 0 here as the permeability, magnetic permeability of the magnet in free space or vacuum or air. Okay, now please remember it that this is called the Coulomb's law. This is the Coulomb's law of magnetic force. Please remember it. We found it, we already did Coulomb's law in case of charges, electrostatic charges. Now we are doing Coulomb's law of magnetic force. So this is the Coulomb's law of the magnetic force between the two poles of a magnet. Clear? Now for example, if M1 is equal to M2 equal to M, that means if the pole strengths are same and the distance between them is 1 meter, So please remember F is coming 10 to the power minus 7 Newton. F is coming 10 to the power minus, and F we have taken as 10 to the power minus 7 Newton. So this is our F, and this is mu 0 by 4 pi. This is the product of the poles. This is the square of the distance. So what we are getting, that the pole strengths of the two magnets are plus or minus 1. Pole strengths of the two magnets are either plus 1 or minus 1. So when can we say that? That if the poles are equal, say m, distance between them is 1 meter, force is 10 to the power minus 7 Newton. Okay, so putting it in the force formula, we are getting what is the value of the m? It will be plus or minus 1. Thus, strength of magnetic pole is said to be 1 ampere meter. So this is what 1 ampere meter. Please note that this is ampere meter. So when can we tell this is 1 ampere meter? When the force of attraction or repulsion is 10 to the power minus 7, and the two poles are separated by a distance of 1 meter, and the poles should be of similar poles, strength should be similar, and placed in vacuum at a distance of 1 meter, and the force of attraction is 10. So then only 10 to the power minus 7. So then only we can tell that the two magnetic poles are said to be 1 ampere meter. Okay. So next we are dealing with magnetic field lines. Magnetic field lines. So what are these magnetic field lines? They are imaginary curve, the tangent to which at any point gives us the direction of the magnetic field at that point. So see, these are the magnetic fields which are coming out from the North Pole. This is the North Pole, okay, coming out from the North Pole, and this is the South Pole, as you can see. So lines are entering the South Pole, lines are entering the South Pole, and lines are coming out of the North Pole, coming out of the North Pole, and this is North Pole to South Pole, as you can see here. This is in case of a magnet. Similarly, magnetic field due to a solenoid carrying current, solenoid carrying. So this was the solenoid which is carrying current. So here is the magnetic current is flowing like this. This is the current flowing. This is the current flowing. Mind it. This is the current flowing through the solenoid. This is the solenoid. Okay. So this is the magnetic field which will be formed around the solenoid. Similarly, electric field lines due to a electric dipole. So here is a dipole, plus and minus. Okay, so from the plus electric field lines are coming out, from the minus electric field lines are entering. So this is the electric field which is created. And in the magnetic lines, at any point, if I draw a tangent, that will give me the direction of the magnetic field, in which direction the field is there. So if I draw a tangent here, it will tell me magnetic field is in this direction. If I draw a tangent here, it will tell me magnetic field is in this direction. So the tangent at any point will give us the direction of the magnetic field. Clear? Next is properties of magnetic field lines. So what are the properties of the magnetic field lines? They formed closed continuous loops. Closed. Outside the body of a magnet, the direction of magnetic field lines is from North Pole to South Pole. As you see, outside the magnet, it is North Pole to South Pole here. At any given point, tangent drawn to the magnetic field lines represent the direction of the magnetic field at that point. So as you can see here, that if I draw a tangent here, in this, then I can find the direction of the magnetic field. The magnitude of magnetic field at any point is represented by number of magnetic field lines passing normally through unit area around that point. That means if there is a area of 1 meter square So normally how many magnetic lines are passing through this area gives the strength of the magnetic field. Clear? No two, please note here, no two magnetic field lines can intersect each other. Okay, this is a very important topic. No two magnetic lines can intersect each other, because if they do, if the two magnetic field lines will intersect, this is a magnetic field line, this is a magnetic field line, if they intersect at this point, so if I want to draw a tangent, I can draw like this, and for this line it will be like this. So at the same point there are two tangents drawn, which shows that magnetic field has two directions, which is not possible. So magnetic field at a given point can have only one direction. So that is why magnetic field lines cannot intersect each other. Next, we are dealing with magnetic dipole. So what is a magnetic dipole? A magnetic dipole consists of two unlike poles of equal strength. One equal strength, unlike poles. That means one is a north pole, one is a south pole, and separated by a distance between them, and separated by a small distance between them. So it is a vector quantity and directed from south pole to north pole. This is the magnetic moment, south pole to north pole. This is the magnetic moment, south pole to north pole. And what is its magnetic dipole moment? What is a magnetic dipole moment? Magnetic dipole moment, it is the product of the magnetic strength and the distance between the two poles. It is the product of the magnetic strength and distance between the two poles. That is the, and its SI unit is ampere meter. SI unit is ampere meter. Clear? So let's move ahead with the next one. The next one, magnetic field strength at a point due to a bar magnet. So this is what we are going to study, the magnetic field strength at a point due to a bar magnet. Magnetic field strength at a point due to a bar magnet. Okay, so let's see what is there. So first of all, when the point lies on the axial line of the magnet, here is the point, and this is the axial line. This is the axial line. So we have to find the magnetic field strength at this point. Okay, so this is the magnet having equal pole strengths M and M, separated by a distance 2L, and from the center the distance is D. So as we know, the magnetic field strength at P due to the north pole will always be directed away. So this is the magnetic field strength due to the north pole. So it will be mu0 by 4 pi. Here a pole strength of 1 is kept. So what is the force? That is, this is the magnetic field strength at a distance of D minus L, isn't it? So this will be D minus L. And this will be D plus L. D plus L. So as you can see, friends, here that due to the north pole, the magnetic field at P, due to the north pole, the magnetic field at P is mu0 by 4 pi M into 1, because this is M and here is 1. Okay, so, and the distance is D minus L whole square. So it will be along NP because it is a north pole. Similarly, due to the south pole, so it will, the distance is D plus L. So it will be mu0 by 4 pi M by D plus L whole square. And because it's a south pole, it will be towards P to S, okay, from P towards S, towards the south pole. So the net magnetic field strength will be B1 minus B2 because they are opposite directions. This is along NP, this is along PS, okay. So as you can see the calculations here, so if we do the calculations, so you can easily see that ultimately they will give you this part, okay. So 4LD can be written as M into 2L, here M into 2L, this is that M into 2L into 2D, and M into 2L is magnetic moment. M into 2L is the magnetic moment into 2D. So if the length is, if your L is very less than D, if your L is very less than D, as you can see, this is the D, this is the D, and this is the 2L. So if your length is very less than D, so what we can do is that we can neglect the D part, we can neglect the D part from here, the L part from here, we can neglect the L part from here. So it will become D4 and up is D. So this is the formula along NP, along NP. So this is the formula of the net magnetic field due to a magnet having equal pole strengths, okay. So it will be always from south pole to the north pole, south pole to the north pole. The magnetic field strength along the axis will be south pole to the north pole. So this is along the axis. Now we are doing magnetic fields at a point on the equatorial line of the magnet, on the equatorial line of the magnet. So let's see what is there. So as you can see here, this is the magnet, and I want to find out at a distance of D along the perpendicular bisector. So this is called the equatorial line, okay, at a distance of D, and this will be, this is L, this is L and L, and this will be root over L square plus D square. This is the distance. This also will be root over L square plus D square. So here we have to find the magnetic field due to the dipole along the equatorial line. So first, due to the north pole, as you can see, north pole means it will go away from the north pole, it will go away from the north pole. So this is the magnetic field due to the north pole along NP. Similarly, due to the south pole, it will go towards the south pole, it will go towards the south pole, clear, and it is this. And now as well along PS, as you can see, and this is along NP, this is along PS. Now please watch here, this B1 will have two components. This B1 will have two components. One is, this is the B1 sine theta, and this is along this, it will be B1 cos theta. Similarly, due to the B dash, it will be along this, it will be B dash sine theta, and here along it will be B dash cos theta. So that means, as you can see here, the sine theta component cuts out, the sine theta component cuts out, the sine theta component cancels out. So only the horizontal component B cos theta will be acting along the NS, north to south, north to south. It was here south to north, and here it is north to south, and they get added up. So net magnetic field will be B1 cos theta plus B2 cos theta. So because B1 and B2 are same, as the pole strengths are same, so B1 and B2 are same. So this is that B1 or B2 twice, because the B is same, and this is that cos theta, this is that cos theta, base by hypotenuse, okay. So calculating it, we get this. And now m into 2l is actually what? Magnetic moment. M into 2l is the magnetic moment. So this is the formula. This is the formula for the magnetic field along the equatorial axis. Along the equatorial axis. This is the magnetic field along the equatorial axis, acting along px. That means north to south. North to south. Now the question is here that if the length is very small than d, if the length is very small than d, then what happens? Neglecting it, and we get this. So please note here, this is the magnetic field due to a magnet along the equatorial axis. Along the equatorial axis, this is the magnetic field along the equatorial axis. And this was the magnetic field along the axial line was this. Magnetic field along the axial line was this. So as you can see, if I do magnetic field along the axial line to the magnetic field along the equatorial line, you will see it's coming 2:1 ratio. Okay, this is a very important formula. Please keep a note of this. Next, let us do one sum. There is a magnet of 2 centimeter length. Pole strength, so this is the M. Find the magnetic field strength at a point on its axis at a distance of 20 centimeter. That means D is 20 centimeter. D is 20 centimeter. Okay. So this is the formula for the axial magnetic field. This is the formula for the axial magnetic field, as you all know. Axial magnetic field. Okay. So using mu 0 by 4 pi is 10 to the power minus 7. 2 into m. This is the m. What is m? M is actually what? M is m into 2l. M into 2l. Okay. So here m is given as 60 and 2l is given as 2 centimeter. 2 into 10 to the power minus 2. So using those, and this is the distance d. So we are getting this much Tesla. Similarly, now they are telling that what is the magnetic field if I take it at the same distance on the equatorial line. So we know that B axial by B equatorial is actually twice. So B equatorial will be twice of the magnetic B axial by 2. So if I do this, I am getting this is the magnetic field due to the equatorial at the equatorial line. Clear? Next, friends, let us see current loop as a magnetic dipole. Current loop as a magnetic dipole. So watch here. In this part, this is a loop. This is a loop. And here is the current flowing. Here is the current flowing like this. Here is the current flowing. So if you look from the upper surface, if you look from the upper, this is the surface area we have taken. That means we have taken an upper, and this is the loop of area A. So if you look from the upper surface, the current is flowing anti-clockwise, which will give me a north pole. Anti-clockwise means north pole. But if you look from the bottom, the current will seem to flow clockwise, which will give you south pole. Now upper part is north pole, the lower part is south pole. That means it behaves as a magnet and also as a magnetic dipole. Now if you behave as a magnet, you have to behave as a dipole. You have to behave as a magnetic dipole. So the upper part is acting as a north pole. So this part is acting as a north pole, and the lower part will act as a south pole. So this whole combination, current loop. So this current loop will behave as a magnet. Okay, and what is the magnetic dipole? What is the magnetic dipole of this magnet? What is the magnetic dipole? The magnetic dipole is M equal to NIA, where N is the number of turns, I is the current, A is the circular loop's area. So this is the magnetic dipole moment, M equal to NIA. Now here the unit vector is directed along this direction. See, that means it is perpendicular to the surface. It is perpendicular to the surface. The unit vector, the direction of the magnetic dipole is perpendicular always to the surface. Please remember it. The direction of the magnetic dipole is always perpendicular, so it's a vector quantity. And how we do? We detect it by the right hand screw rule. Right hand screw rule. That means if you screw up like this, that means you are going up, and if you screw up like this, that means you are going down. So this is the right hand screw rule. Next we are going to study the torque acting on a bar magnet in a magnetic field. Okay, so let's see. That means if I place a magnet in a magnetic field, what is the torque acting on it? What will be the torque acting on it? So let's see here. So here is a magnet kept. As you can see, this is a magnet, north and south pole kept. Here is a magnet with north pole and south pole kept, inclined at an angle of theta. Inclined at angle of theta. Okay. So the north pole of the magnet, and this is the magnetic field. North to south is the magnetic field. This is the magnetic field. North to south. Okay. So if I put it at an angle theta, the force of the north pole will try to act towards the south pole with a force MB, and south pole will get attracted towards the north pole with a force MB. Okay, now what is the torque acting on it? So see, torque, equal and opposite forces produces a torque. Equal and opposite forces will produce a torque. So torque is the force into the perpendicular distance. Okay, now this torque will try to rotate the magnet. This torque will try to rotate the magnet like this and put it in an equilibrium position along the direction of the magnetic field. Put it in the equilibrium position along the direction of the magnetic field. So the torque is the force into the perpendicular distance. So what is this NA? This is the perpendicular distance. As you can see, this is the perpendicular distance, which is coming at 2L sine theta. 2L sine theta. So this is the torque acting on it, and M into 2L is the magnetic dipole moment. M into 2L is magnetic dipole moment. So MB sine theta means it is M cross B. So please watch here. This is the torque acting on the magnetic bar, and the direction of the torque is perpendicular to the plane containing the M and B, and is given by right hand screw rule. So please note here that direction of the torque, that will be that right hand screw rule. If you go up, the torque will act like this, and if you go down, the torque will act like this. So the direction of the torque is given by the right hand screw rule. Right hand screw rule. This is very, very important. The direction of the torque is given by the right hand screw rule. Clear? Next, see the potential energy of a magnetic dipole in a magnetic field. Potential energy. So please watch here that if there is a torque acting and it is rotating, that means there will be some energy stored in the magnetic dipole. So let's see. Let the torque rotate it through a small angle d theta. Let it rotate through a small angle d theta. So what is the work done? This is the force acting, restoring torque into d theta. That means I can write like this. So if now I try to rotate it from theta 1 to theta 2, so what is the work done? The work done will be this. I will integrate it from theta 1 to theta 2. MB is a constant. Sin theta integration is minus cos theta. So it will become minus cos theta 2 minus cos theta 1. Now if theta 1 initial angle is 90 degree and theta 2, that means from 90 degree it has been turned to an angle theta. From 90 degree it has been turned, initial angle was 90 degree and it has been turned. That means, please watch here, the bar was like this. This is the magnetic field. The bar was initially 90 degree and now it has been turned by an angle theta. So this is the work done, and cos 90 is 0, so it is this minus m dot b. So it is a scalar quantity, and the negative sign suggests that the energy is stored in the bar, in the magnet, because it's negative, energy stored. Next, come to special cases. So in the special cases, if theta is 0, we know cos 90 will be 0. So no work will be done. No work will be done if I am turning the magnet from initial angle 90 to another angle 90. Okay, from initial angle 90 to another angle 90, if I want to turn it, that means no work will be done. Second, if theta is 0, W is minus MB. So this is the maximum potential energy and it is in the stable equilibrium. It is in the stable equilibrium. That means you are bringing it to the along the direction of the magnet. You are bringing it along the direction of the magnet. And if theta is 180 degree, W equal to MB. So potential energy is maximum. Here it was minimum in 0 degree. And this is the unstable equilibrium. This is the unstable equilibrium. Clear? Next, a very important topic, that is Gauss's law. We have already done Gauss's law in electrostatics, and now we will do Gauss's law in magnetostatics. So what is that? The net flux, this is phi, through any closed surface. So see, this is a closed surface. Okay, closed surface. The net flux through any closed surface is always 0. Please note here. That means over any closed surface, if you want to find out the net flux, flux is B dot ds. This is the flux. Okay, this will be 0. Please remember here. Net flux through a closed surface, magnetic flux passing through any closed surface will be always 0. There will be no magnetic flux created. And this theorem states that monopole do not exist. Magnetic poles always exist in unlike pairs of equal strength. unlike pairs. Magnetic fields exist as unlike pairs of equal strength. Please note it here. Monopoles do not exist, and magnetic poles always exist in unlike pairs of equal strength. Next is features of the Earth's magnetic field. Please watch here. Features of the Earth's magnetic field. What are the features of the Earth's magnetic field? First of all, watch here. This is Earth. This is Earth. This is the geographic north and south pole axis. Geographic north and south pole. This is the south pole geographic. This is the north pole geographic. And this is the magnet which we feel inside. So this is the south pole and north pole, and this is the magnetic north pole axis and the south pole. So this is the magnetic south pole and this is the magnetic north pole. Clear? Right? And this is the magnetic equator. This is the magnetic equator. Clear? If this is the magnetic equator, then this is the geographical equator. This is the geographical equator. This is the geographical equator. Clear? So now let's see what is magnetic declination. What is magnetic declination? So what is that? The small angle between magnetic axis. So here is the magnetic axis. Okay, and here is the geographic axis. This angle is called the magnetic declination. Okay, this angle is called the magnetic declination, and it is also the angle between magnetic meridian and geographic meridian. What is magnetic meridian and geographic meridian? A plane drawn along the magnetic axis is called the magnetic meridian. This is the magnetic meridian, and the plane acting along the geographic meridian will be called the geographic meridian, and the angle between them, this angle is called the magnetic declination. Magnetic declination. Clear? So here what do we have to see? Next, magnetic dip, that is this angle, or magnetic inclination. What is that? It is the angle which the total direction of total Earth's magnetic field makes with a horizontal line in a magnetic meridian. So see, this is the meridian. As you can see, this is the meridian. This is the magnetic meridian. And what I am telling, it is the angle which the direction of total Earth's magnetic field. This is the total Earth's magnetic field. This is the total Earth's magnetic field. I'll show you. This is the total Earth's magnetic field, and the angle which it makes with the horizontal. Angle which it is making with the horizontal. This is the horizontal. Okay, total Earth's magnetic field making an angle with the horizontal of the magnetic meridian. That is magnetic dip. Clear? And the horizontal component, as you can already see here, horizontal component is what? It is the component of the total intensity of Earth's magnetic field in the horizontal direction in the magnetic meridian. In the magnetic meridian, the horizontal component of the Earth's magnetic field. So we can write that it will be H will be R sine sigma V will be the vertical component of the Earth's magnetic field is R sine sigma. Horizontal component will be R cos sigma. Okay, and the resultant magnetic field will be given by this, and tan sigma will be given by V by H. Please note here, these are important formulas. You have to remember these. H equal to R sine sigma, V equal to H equal to R cos sigma, V is R sine sigma. This is the magnetic dip. This is the magnetic dip. Okay, and please remember one thing, that is at the magnetic poles, as you are already seeing here, at the magnetic poles the sigma will be 90 degree. So horizontal component will not be there. Horizontal component will not be there. Vertical component total. Earth's field will be the vertical component. At magnetic poles theta is 90 degree, and at the magnetic equator the sigma is 0 degree. So it will be totally horizontal field and no vertical field at the equator. Okay, so please keep note of these important topics. Next, a very important sum, that is if theta 1 and theta 2 are the apparent angles of dip. So dip, what is the dip? That the Earth's total Earth's magnetic field makes with the horizontal component of the in the magnetic meridian. Theta 1 and theta 2 are the angles of dip, so I can tell that tan theta 1 will be V by H1 and tan theta 2 will be V by H2, and in two vertical planes at right angles to each other, and we have to prove this. And tan theta is V by H. So let's first see from here, that is from here what we can write down, H square equal to H1 square plus H square will be H1 square plus H2 square. Okay, please remember this. The horizontal components, this is the horizontal component, this is the Earth's magnetic field tan sigma, this was the sigma, this was the theta, and this is the vertical V. So if it is theta 1, as you can see, if it is theta 1, okay, this is the R. If this is the theta 1, so what we can write, H1 will be H1 tan theta 1 will be what? V by H1. Okay, V by H1. And if it is theta 2, suppose this is theta 2 and it gives you H2, so tan theta 2 will be V by H2. And now you can easily see from here, this was RH, this was the H. So this H, this is H1, this is H2. So how are they connected? H square equal to H1 square plus H2 square. So H square is this, H1 square is this, H2 square is this. So it gives you, this is the relation. Clear? Next, if lambda is the magnetic latitude at a place where the dip is same, then please remember it, this is the relation which you have to keep in mind. This is the relation which you have to keep in mind. Lambda is what? The magnetic latitude at a place. Magnetic latitude at a place is lambda. So we can write, and the angle of dip is this, so we can write this is the relation between the magnetic latitude and the angle of dip. Clear? Next, we are dealing with the tangent law. So what is tangent law? Let us see what is tangent law. So when a magnet is suspended under two magnetic fields, please watch here, this is important, two magnetic fields of strength F and H perpendicular to each other. If F is like this and if H is like this, and here is a magnet suspended, these are perpendicular to each other, the magnet comes to rest angle, making an angle theta with the direction of H. That means if this is the theta such that F will be called as H tan theta. This is the tangent rule. F will be called as the H tan theta. F and H are two magnetic fields. F and H are two magnetic fields. Clear? And theta is the angle made by the magnet with the horizontal part. So then we can write F is equal to, or let us please do it like this. Let us make this as H and F. This is our F, this is our H, so this is that theta. Magnet is coming at an angle theta with the horizontal field, so we can write that the F will be H tan theta. And the principle of a galvanometer, the principle of a tangent galvanometer is based on the tangent law. This was the tangent law. Principle of a tangent galvanometer is based on the tangent law. This is the tangent law. This is the formula for the tangent law. Clear? Next, the working. So this is our two magnetic fields F and H, and the magnet is coming at an angle theta with the H. Okay, so we can write F equal to H tan theta. We can write that. And what is F? Mu 0 by 4 pi 2 pi Ni by R. Please note this formula. Mu 0 by 4, the force making at an angle theta is mu 0 by 2 pi, mu 0 by 4 pi 2 pi Ni by R. R is the distance of the magnet from the field. So equating this, we get this, which we can write like this, give the name of A, and A is called the reduction factor of the tangent galvanometer, and his SI unit is ampere. K is the reduction factor, which is H by, so it is H by mu 0 by N mu 0. Please watch the formula here. This is very, very important. So this is the this part is the A, this part is the K, which is called the reduction factor of a tangent galvanometer. SI unit is ampere. So now friends, we have completed the theory part, and now we will be moving on to the numerical section. We will now move on to the numerical section of this chapter. So let's see. The first sum says the radius of the coil. The first sum says that the radius of the coil of a tangent galvanometer, this is the radius. How many turns of the wire, and I don't know, should be used if a current of 40 milliampere I is producing a deflection of 45 degree theta. I know, okay, theta is given. Horizontal component of the earth is given this. Clear? So we know that there is a formula. This is the force acting on the this is the force acting at the center will be what? Mu 0 by this is the due to the straight wire is mu 0 I by 2 pi, mu 0 I by 2 pi. This is the for a circular wire, sorry, this is for a circular wire. For a circular wire of radius r carrying current I, the magnetic field at the center will be what? How much? Mu 0 I by 2 pi, and for n turns it will be n. We have already done that. So this is that formula, and that is the perpendicular magnetic field, which is the H tan theta. So from here all the datas we know that, putting it we get n equal to 229 turns. Next sum, a magnetized wire, steel wire length, this is has a pole strength, this is m, bent into a semicircle, though this is a semicircle. Calculate the magnetic moment of the needle. Okay, magnetic moment of the needle. So see, this is a semicircle of radius r. This is the magnetic moment of the ends. So we know pi r is the semicircle circumference, which is given 31.4. So radius of the semicircle is 10. Excuse me. So magnetic moment m is equal to m into 2l, and here 2l is acting as 2r. This is the total length. So m I know and the r I know, so we get the magnetic moment of the needle. Clear? Next, two magnetic poles, one of which is 4 times the other. That means m1 is equal to 4 times of m2, or m2 equal to 4 times of this. Exerts a force of 10 gf. So this is the force given when placed at a distance of 10 centimeter in air. That means this is the r given. Find the strength of each pole. That means pole strength they are asking. So this is the force formula, and it is given 10 to the power minus 2 gf, so into 9.8 Newton. Mu 0 by 4 pi is 10 to the power minus 7. One is 4 times of the other, and distance given. So calculating, we are getting this is the magnetic pole strength of the magnet. This is the magnetic pole strength of the magnet. Next, friends, let's see the sum. Two identical bar magnets. So here is a bar magnet, each of length L. So you can see L and L, two bar magnets, pole strengths given M, are placed at right angles with north pole of one touching the south pole. So here you can see north pole of one touching the south pole of one. All the pole strengths are M, M, M and M. These are the pole strengths, lengths given. Find the magnetic moment of the system. Okay, this is the magnetic moment of the system they're asking. So what is the net length of the magnet? This L root 2, and magnetic moment is M into distance between the two poles, which is this. Okay, from S1 to N2 is the direction. Two identical magnets with length given, weight given, are each arranged freely with their like poles facing in a vertical glass tube. So like poles, okay, so there will be a repulsion, there will be a repulsive force between the two magnets, which will balance the weight of the magnet. So F is equal to mg. This is the repulsive force, which is balancing the thing. Okay, this is the magnetic pole strength, and this is the weight of the magnet. Putting it, we get the magnetic pole strength as this. Similarly, the magnetic field, please watch here, the magnetic field at a point 10 centimeter away from the magnetic dipole is found to be this. Find the magnetic moment of the dipole if A is end-on position. First, they are telling that if your point is here, (10 centimeter), and the second case they are telling if your point is here, 10 centimeter away. So this is the end-on position, whose formula is magnetic field is given by this, the axial position, and this is the equatorial position, broadside. So the magnetic field is given to us, end-on position, only M I don't know, so we can calculate it. Similarly, the broadside on position, the formula is this. This is the D. Okay, so the formula of the M will be this. B I know, 4 pi by mu 0 is 1 by 10 to the power minus 7, and this is the D given, so we can calculate it. This is the magnetic field at that point, equatorial point. Okay friends, let's now see the next one. Find the magnetic field due to a bar magnet 2 centimeter long. So length is given, pole strength, that means the M given, at a point 10 centimeter from each pole, that means this is 10 centimeter from each pole. From each pole it is 10 centimeter. So that means I can find out what is OP. OP will be this, and it becomes the equatorial formula. The formula is about the equatorial, where this M is actually, the M is actually M into 2L. So putting all the values, the length of total length of the magnet is given to us. This is the 2L. Mu 0 by 4 pi is 10 to the power minus 7. We have used it. And OP, the distance, is given to us. So calculating it, we are getting this is the magnetic field. Similarly, the magnetic field at a point on the magnetic equator, this is the magnetic field, equatorial point we know. If the radius of the earth is 6400 kilometer, find the magnetic moment. That means we will use the equatorial formula, magnetic field due to equatorial. Okay, so B I know, only M I don't know, the radius I know, mu 0 by 4 pi is 10 to the power minus 7 I know. So putting this, we calculate the magnetic moment at the center of the dipole. Next is, we will use this, the magnetic dipole moment of the earth. So this is the M, dipole moment M, M I know, and current I don't know, radius I know, that means area I can find out, pi r square. This is the pi r square formula, pi into r square, and we will take it as n as 1, number of turns is 1. So from here we can calculate the current flowing. Similarly, a bar magnet is suspended in a region where it is acted upon by two fields. These are the two fields at an angle of 60 degree, and here is a bar magnet. Now it is in equilibrium at an angle 45 with one field and 15 degree with another field. So because it is in equilibrium, so the torque acting due to both the magnetic fields on the bar magnet will be same. So this is the formula of the torque. So we can find out the magnetic field of the first one, the second one. Magnetic field is given to us and the angles are known to us, so we can find out the first magnetic field. Next, friends, they have given there are two magnets of magnetic moment. One is this, one is this, one is this, one is this, are joined to form a cross. This is the cross. The combination is suspended freely, and in the equilibrium it makes theta with the field. So see here, it makes theta with the magnetic field. This is the magnetic field. It makes theta. So torque due to both, this is 90 minus theta. So torque due to both the magnets should be same because it is in equilibrium position. So this is the torque due to first magnet, this is the torque due to second magnet. Here is the magnetic moment of the second magnet, first magnet. Solving it, we get theta is 60 degree. That means the magnet was inclined at an angle of 60 degree with the first magnet. A circular coil of 50 turns, N is given to us. Diameter given, so radius I know. Current given. How much work is done in rotating the coil through 180 degree. That means initially it was 90 degree and finally it was 180 degree, and using the formula of the work done, cos 180 is minus 1, cos 90 is 0. This is our formula, and this is that M, magnetic moment, and B is given to us. So we calculate the work done. Next is a straight solenoid of length given, 1000 turns given per 1000 turns per meter. Okay. Area given. It is placed at 30 degree with a magnetic field B given. Find the torque when the current I given passed through it. So this is the formula of the torque. M is NIA. All the N given. N is 1000 turns per meter. So what is the total length? Total length is 50 centimeter, means 0.5 meter. So on a 0.5 meter there are these many turns. N. This is I, this is A, pi r square. This is the B, and this is sine 30. So this is the torque acting on the solenoid. A circular coil of 100 turns, N I know. Radius I know. Current I know. Find the work required to turn external field I know, B, through 180 degree about an axis perpendicular to the magnetic. So that means it was starting from 0 degree to 180 degree. They are telling coil is initially at right angles to the magnetic field. That means this was the coil, this is the magnetic field. As you can see that the plane of the coil is perpendicular. The coil is initially at, this was the coil right angle. That means the normal is making an angle 0 degree. The normal is making angle 0 degree. So theta 1 was 0 degree. And now through 180 degree. That means the coil will, this, if this is the AB, it is now turned through 180 degree. So this is the A and B, and this angle is 180 degree. Okay, So we are putting the values, cos 180, cos 0. Calculating area, we can find area is pi r square. So this is the work done. Next, at a certain place, the angle between geographic meridian and the magnetic meridian is 58 minutes. Geographic meridian and magnetic meridian is called the angle of the declination. That means this. Vertical and horizontal magnetic fields are given to us. This is the vertical and horizontal. So we get 1 by root 3. So sigma comes out to be 30 degree. Find the declination angle. Find the angle of declination and the angle of dip at that place. Angle of declination is given to us this. The declination at a place is 20 degree west. 20 degree west, towards west side. So you can see this. This is the magnetic north pole inclined 20 degree towards the west. This is the angle of declination. In what direction should a ship be steered so that it reaches geographic north east? Geographic northeast means this is 45 degree. Okay, that means the total angle is 65 degree. So 65 degree east of magnetic north, it has to turn. It wants to reach from here to here. That means it has to come through an angle of 65 degrees. Next, the horizontal Earth's magnetic field is 0.2 Gauss. So H I know. And the total magnetic field R I know. So find the angle of dip. Angle of dip. So this is the angle of dip. Similarly, a magnetic needle is free to rotate in a vertical plane, which makes 60 degree with the magnetic meridian. Okay. The plane is making 60 degree with the magnetic meridian. If the needle stays in a direction making an angle of tan inverse 2 by root 3 with the horizontal, what would be the true dip at that place? So please watch here. Vertical plane is making 60 degree with the magnetic meridian. Okay, if this is the magnetic meridian, the vertical plane is making an angle of 60 degree with the magnetic meridian. Clear? So here we can say, if the needle stays in a direction making an angle tan inverse 2 by root 3, tan inverse 2 by root 3 with the horizontal, that means the needle is making an angle with the horizontal. That means this tan inverse 2 by root 3, this angle. Clear? So we can easily tell that tan of that tan inverse 2 by root 3 is V by H. We can tell that. So 2 by root 3 will be V by H. This sigma is given to us. This is that angle. Okay. And they are telling that it is making an angle 60 degree with the magnetic meridian. So please watch here one thing. Cos 60 is half, and this angle is making 2 by root 3. So tan sigma will come 1 by root 3, which is getting 30 degree, which is giving you 30 degree. This is the true angle of dip at that place. True angle of dip at that place. Clear? So now next sum. Two short magnets placed horizontal and perpendicular to the magnetic meridian have their north poles 30 centimeter east and 20 centimeter west from a compass needle. If there be no deflection in the needle, then compare their magnetic moments. Now see here one thing. Two short magnets placed horizontal and perpendicular to the magnetic meridian. That means in the magnetic meridian, this is a magnetic meridian, I am placing one magnet horizontal and one magnet perpendicular, like this. Sorry, not like this. Okay, so the other one is actually like this, perpendicular, that means like this, 90 degree. Okay, with the north poles 30 centimeter east and 20 centimeter west from the compass needle. If there be no deflection in the needle, compare their magnetic moment. So that means the magnetic field acting on the first magnet and the second magnet should be same. So this is the equatorial magnetic field. The distances of the magnets are given to us, 30 degree, 30 and 20, which is 27:8. This is the comparison of their magnetic pole magnetic moments, M. There is a magnet 15 centimeter long, here you can see. Pole strength this, so this is M. Find the magnetic intensity B at a point 20 centimeter directly above the north pole. So here I have to find the magnetic field 20 centimeter above the north pole. This is 15, so this will come out to be 0.25 meter. This will come out to be 0.25 meter. Okay, now here please watch one thing. At this point, due to the north pole, the magnetic field will go away, and due to south pole, the magnetic field will come in toward the south pole. So due to the north pole, the magnetic field is this formula, which is this, and due to the south pole, the magnetic field is this formula, which is this. So watch one thing. This BS has two components. One is BS cos theta, one is BS sin theta. Okay, so the vertical component BS cos theta is coming out to be this. Theta can be found out easily, cos theta, and net resultant vertical component will be 625 minus this, because they are opposite directed, and the horizontal component is given as this is the net vertical component, clear, and horizontal component is BS sin theta, that we have to calculate it, BS sin theta, which will come out to be 240 micro Tesla, and then find out the resultant of that, which is this. Okay, so BS already we know, sin theta we can easily find out, BS already we know, and sin theta we can easily find out, which is the perpendicular by the hypotenuse. So we can get BS sin theta, and we can get the component. Now find the resultant. Next sum, there are two short identical magnets, as you can see, one magnet, two magnets magnetic moments are given to us. This placed 10 centimeter between them, that means this is 10 centimeter. Okay, such that their axes are perpendicular. Yes, their axes are perpendicular. Find the magnetic field at a point midway between them. So here we have to find the magnetic field first. Axial magnetic field 10 centimeter away. The formula is this. Axial magnetic field, mu 0 by 4 pi is 10 to the power minus 7. Magnetic moment is given to us. Distance is given to us, which should be 5 into 10 to the power 5. Okay, so this distance is given to us. Midway between the two magnets, separated. This is okay, 1 minute. Here I have to find, so this distance is 5 centimeter. This is 5 and this is also 5. So here we can find out, this is the magnetic field along O1P, because it acts always from the O1P, North Pole. Similarly, for the second magnet, it is the equatorial formula we will use. Distance is again same. So we can find out it will be along PB2. PB2. Okay. This is PB1. And now we can find out the resultant magnetic field. We can find out the resultant magnetic field and the angle also. This is the angle. Clear? So friends, with this we have completed the chapter of the magnets and earth magnetism, and I hope you have understood it. Please, you should do one thing, that is you follow it along with me and keep practicing, and before doing the numericals, please follow the notes and the lectures which I am giving here. You have to study them, you have to see the videos quite often, 2-3 times at least you will see the video, and then only you will get the concept before you do the sums. Okay, so my request is please first go through the videos very nicely and then only try to attempt the numericals. Okay, so that is all for today's class. Hope you have understood it, and if you have understood, please subscribe to the channel Parijat Sir Classes. Please subscribe the channel, okay, so that I can get motivation to make more videos for you. So that's all for today's class. It's thank you very much from my side.